Well, for those who don't know me, my name is Palandram Sundar, and I'm with the Design and Manufacturing Center. And ladies and gentlemen, it's my privilege to welcome you all to UTT and this seminar that we're having. Now, before we proceed, I'd like to introduce Ms. Sharon Narayan-Scores, who will give a bit to us about the safety requirements for the seminar.
Good morning and welcome to University of Trinidad and Tobago, O'Mara campus. I indulge your attention as I share a minute of safety with you. Kindly note that we have no evacuation drills planned for today. In the event of an emergency, you will be notified verbally. If there is a need to evacuate, we ask that you follow these instructions. Take your personal belongings and calmly proceed to the nearest exit. Please note that the exits are labeled in red. Once outside, head directly to muster point 1. This muster point is located north of the main building, right of the guard booths, at the entrance. At muster point 1, please await further instructions. Your host will be responsible for you at the muster point. Kindly note that the washrooms are located at the back of the building. Thank you. We hope you find today's seminar very enlightening.
Thank you, Ms. Narayan-Scores. Now, ladies and gentlemen, as part of our ongoing trust in introducing new technology to Trinidad and Tobago, the UTT has been conducting a seminar series in which cutting-edge research and development has been presented. We're fortunate today to have with us Professor Christopher Niezrecki of the University of Massachusetts Lowell to present his work on digital image correlation as applied to structural dynamics, structural health monitoring, and wind energy. Professor Niezrecki is a full professor in the Department of Mechanical Engineering at the University of Massachusetts Lowell. He leads the Wind Energy Research Group and is also the co-director of the Structural Dynamics and Acoustic Systems Laboratory. Some of the highlights of his distinguished career include the use of piezoelectric actuators to actively control mechanical vibrations and the noise within expendable launch vehicles, creation of accurate analytical and numerical methods of the sound radiation of vibrating structures, use of smart materials to actively isolate the vibration of parallel platform mechanisms. Currently, the professor is working in areas of wind turbine blade dynamics, structural dynamic and acoustic systems, smart structures, controls, signal processing, structural health monitoring, and smart materials. And I'm sure in his talk to us today, he's going to give us some bits of details on some of these areas. Ladies and gentlemen, it's my pleasure to present to you Professor Christopher Niezrecki.
Thank you very much. So thank you, Colin, for inviting me. And this is my first visit to Trinidad. So we arrived. This is my wife Amy, by the way. And we've arrived last night. And I'm going to talk about some of the things that we're working on within our laboratory pertaining to structural dynamics and specifically digital image correlation. There's quite a few different applications for this technique, not just for vibration, but for solid mechanics and for energy and wind energy and structural health monitoring. So I'll talk about some of those things today. As I said, I'm a professor of mechanical engineering at University of Massachusetts Lowell. Just to give you a little background about our university, we have approximately 15,000 students. We're located about 30 miles northwest of Boston. So it's about a half an hour from Boston. And let's see. What I'd like to do also acknowledge is the work that I'm presenting today is not just my work, but is also a collaboration between one of my colleagues, Peter Avidable, and all of my students, and also Trillion Quality Systems. So let me talk to you about digital image correlation. First of all, it is a three-dimensional non-contacting measurement technique. It relies on a pair of stereo cameras like this. Commercially available systems exist and are sold. We're using one. This is a system that we use called Aramis. It measures basically surface shape, and from it you can get deformation, strain measurement, And it can be measured at the rate at which the cameras, so it's limited, the speed at which you take the measurements are based upon how fast the cameras can sample. So with it, you can analyze surface shape, you can analyze deformation, and you can get dynamic response. And so primarily what we're interested in as a structural dynamics laboratory is how we can use this technique and how we can exploit it for vibration measurement as well. It can also operate in real time to about 10 hertz. So digital image correlation had its foundation back in the early 80s, and it started with Mike Sutton from University of South Carolina. They primarily used it in the field of solid mechanics, and that's where it's mostly been used for many, many years. And up until recently, people have started looking at this technique for other things, high-speed applications, and now we're trying to exploit it for structural dynamics and wind energy. So let me tell you a little bit about the process or the technique itself. And so, for example, if you have an object that you're trying to image, let's say it's a camera or something like that. You're taking a picture with a camera. Well, what happens? You have the surface here. Light gets illuminated. It goes through an image plane, basically. This is your camera, and you have basically a pixel that occurs on a digital camera. And all of you guys have digital cameras now on your phones or in a camera. So this is what happens. So let's say you have an image like this. And if we zoom in on this little box right here, we'd like to represent that as a digital image. Okay? So what we're going to do is we're going to represent the pixels, each pixel, on a grayscale from 0 to 255. If it's a higher number, if it's perfectly white, then that number is 255. If it's perfectly black, then that number is 0. So we can represent this little box, which is that portion, by this set of numbers. And that basically is the digital image. Okay? So what we'll get is a pixel array that looks something like this if we plotted it in terms of height. And what you have to do afterwards is to apply a little bit of filtering, and this technique uses filtering, I'll talk about that, to smooth out that image. So if we zoom in, let's say we have an area that's like this. We've got this cross pattern here. And now let's say that this, if we look at this box here, and let's call that little box a facet, okay? So we can represent this. So 0 represents a black image. 100 represents a very light image, like white. And so we have this facet here. Now if that facet moves over and up, well, I can take that whole image and I can correlate. I can say, I can look at all the different pixels and those numbers, and I can say, well, this set of numbers is most correlated to that box. So that, what happened to the structure was that it moved from here, it moved over 1 pixel and up 1 pixel. Okay? So with that, we can determine how a structure strains or how the deformation is made. So let's do another example. The pattern shifts 1 pixel up and half a pixel to the right. Okay, so here's our pattern. And so now the image has moved over half a pixel and then up 1 pixel. Okay, so now instead of having a completely black, what the sensor or the camera will measure is it's half black, half white. So what it's going to get is a grayscale. And so that will be represented by a number that's 50. So with this technique, we have resolution that is sub-pixel, and it depends upon the number of bits that you use to record your digital image. So for example, if you're using a 2 to the 8 bits, that's 256. So 0 to 255, you have that resolution in between your pixels. So that affords you, what it amounts to is that you have a technique that has very high resolution. This is another example. What the technique does is it basically looks at these facets. It creates a set of facets based upon these pixels. As this facet moves and deforms, well, we can measure the strain or deformation of that. The facets are typically 15 pixels, and the correlation techniques rely on a pattern matching technique, and it's typically a very proprietary technique based upon the system that you're using. One of the things is the center of each of these facets is iterated to about 1,000th of a pixel. So it's a very accurate technique, and I'll demonstrate that in a few slides. So in summary, what it amounts to is that we need one camera here, we need another camera here. We need to know the distance between those cameras. We need to know that angle between them. If I know that, then I can triangulate this point in space and I can determine, if I know these cameras are here and I know the angle between them, kind of like the way GPS works, I can identify a point in space. Now if that point moves in plane or out of plane, I can determine deformation or changes in shape. If it moves in plane, then I can determine strain on a structure. And so that's what we're trying to do. How do we calibrate these cameras? Get the position. That's done through a calibration process using a certified, basically a calibration panel. And I can talk about that a little bit later on as well. So this is a typical kind of pattern. You can see this is a plate that's here. It's approximately a foot by a foot. This is the pattern that is applied to the structure. In order to do the correlation, you need to have some kind of stochastic pattern that's on the structure. You can also project a pattern on the structure. So it doesn't. We typically apply dots via paint or something like that. But you can illuminate the structure with light and put a pattern on it. So each of these patterns, each of these, let's say, dots, is about 5 to 7 pixels in size. And this is what the left camera will see. This is what the right camera will see. It will take those two images based upon knowing the camera separation and the angle. You can determine, basically, this is what the output that you get. This was a panel that we impacted. This is the shape of the panel, and there's a big indentation right there. So the spatial resolution is not the size of we're not tracking each of these dots. We have sub-pixel resolution based upon that grayscale variation that I talked about before. So that's one way. That's using digital image correlation. We can also track these dots. These are what's called optical targets. And so what we can do is we can track the center of that target to a resolution of about a 50th of a pixel. So the question is, how accurate is when I say a 50th of a pixel or something like that? Let's talk about sensitivity for a second. The primary thing that controls sensitivity of this technique is the field of view. Okay, so if we're talking about it, this axis represents a field of view. So if the field of view is 1.3 meters, let's say it's about like that big, then our out-of-plane resolution is about 25 microns, which is about 1/1000th of an inch, or 1 mil. In plane, it's about 3 times better than that. Okay, so if I took an image that's about this large with my camera, then I can detect changes in that structure to about 1/1000th of an inch. Now, it scales proportionally. If I make that, instead of 1.3 meters, if I made it 10.3 meters, then my resolution, instead of being 25 microns, it's going to be 250 microns. Okay? And so it scales linearly. As far as strain goes, the lower limit of strain measurement is about 50 microstrains. And the technique is dependent upon the calibration process. It's dependent upon pixel noise of the cameras. It's dependent upon post-processing. So let me show you some examples of the way this technique is used traditionally, and then how we're using it within our laboratory. So this is an example. This is a parachute fabric, and what we've done was we've patterned it. And typically when you take a measurement on a structure or something like that, you apply a little strain gauge on it. And you get information on that strain gauge. And strain gauges are typically about that big. Okay? So that gives you information at that point. What we're getting is information. This is a typical image that you would get by using digital image correlation. And so what we were doing in this test, we had a strain sensor right in the middle that was located right about here. And then you would get information right there at that specific location. But with this digital image correlation, we're getting a full field information about what's happening everywhere on the surface. And let me show you a video that demonstrates that. And hopefully this will come up without issue. Okay, good. So this is basically a cylinder of fabric. We've pressurized the inside of it. This is a mechanical testing machine. The crosshead is moving up, and as it moves up, what we're doing is we're measuring the displacement. We're looking at the displacement. You can see the little white dots that are on the cover of the pattern. That's the pattern that we applied to it. And from that, as this tensile test is being applied, we're measuring the displacement. Likewise, we could have displayed strain, and I'll show you that in a minute. But it gives you an idea of how this technique is typically used. And it's typically used in mechanical testing of dog bone specimens for either compression tests or mechanical tests. But if we have a strain gauge on this, you get information at maybe one point. But what we're getting is information over the entire structure. All right, so this is an example of this is an airbag. It's approximately 1.5 meter by 1.5 meter. And so it also gives you shape information. So you can see clearly this is the shape. We were looking at quantifying the performance of parachute fabrics and how they were affected by pressure, and comparing this with models. This is an example of my daughter's face. Okay. My daughter, her name is Anna, and let me show you some of the raw images that we have here. Okay, so this is her pattern. We spent about an hour patterning her face with white, and she was a very good, very patient. And she was a little bit younger at the time. She just had her 9th birthday yesterday. It was the day before yesterday. So anyways, this is her face. Now what we're going to do is we're going to do some sensing on her face and see what it looks like. So that's the raw camera images. That's one image that you would get from one of the cameras. Of course you need two. And so this is the strain pattern from her face as she smiles. Okay? And if we're looking at strain, this is the major strain. So as a person smiles, you can see there's a lot of strain that occurs underneath the lip. And then also depending upon her facial movements and that sort of thing. But it gives you a clear full field vision of what is happening. Now the other things I'll point out is you can see this part right here on the right or left side of her nose. Well, one camera can't see the left side of her nose and the other one can't see the right side of her nose. And so if you don't have both cameras seeing both parts of the image, then you can't get a measurement on that. And so that's one of the, the limitations of this technique. The camera has to be able to see both sides of the image. So if you have a parachute like this, we were testing this in one of our projects for the Army, in these valleys, in these ridges between the folds of the parachute, both cameras can see this, so you get these dropouts that occur. Okay, so that's what those missing areas are. But the reason I show this is because it demonstrates that, well, what we did in this test was we imaged one side, then we rotated the cameras around, and we imaged the whole 360 degrees. And so we stitched those images together. So you can get, using a pair of cameras, you can get a full, shape of a three-dimensional object. As far as structural health monitoring goes, this is a file cabinet, and what we did was we did these tests a few years ago, 4 or 5, and all these tests that I'm showing you are stuff that we've done in the last 4 or 5 years. And when we started out, we were not so good as we are today, at doing these tests. And so some of the tests I'm going to show you later in the presentation are a little bit better, and we won't have dropouts and things like that. Anyhow, what we did was we were exploring, well, how good is this technique? And so this was a file cabinet when we said, let's just shoot it with a little BB gun and see what we can get. Okay? And so that's what we did. We shot this metal file cabinet with a BB gun, and we wanted to see, could we detect the change in the structure after we impacted it? Well, sure enough, this location here is the point of impact. Okay, and if we drew a line like this, actually vertically like this is basically the section line. This shows the indentation of that BB impact. Now, if I was just looking at it, I could barely tell that there was a change in the structure. But what's happening is that this is bowing out. There's a bulge in the structure, and we're getting this indentation that occurs. This is that same composite plate that I showed you earlier. And again, if we drew a section line across, this is an indentation after the impact of that composite plate. Another thing that we did was we applied a heat gun to this metal panel or this file cabinet, and we want to see was it able to detect the change in temperature. And sure enough, this is where we applied the heat gun. Now, if I was just looking at this visually, I would not be able to tell any difference between before and after. And clearly, there's an obvious change, and you can see how the thermal expansion of the material is causing that metal panel to bow out. So, in a nutshell, the next question is, how can we use this technique for dynamic measurement, and why are we exploring this? So first we started using it for static applications, but then I realized this is a powerful technique that has application for vibration measurement. It's essentially non-contacting, except for the pattern that you apply. So there's no mass loading on the structure. And it provides spatially rich information about the structure. So we get a tremendous amount of information over a wide area. It's essentially insensitive to rigid body motion. Okay? So, for example, there are laser vibrometers that exist for measuring structures. And if you bump the laser, then that's going to mess up your measurement. Or if there's a large rigid body motion in the structure, that's going to mess up your measurement too. And so this is fairly insensitive to that. And it's relatively quick too. So I'm going to show you some of the results that we were working on for dynamic measurement. So let's go back to my daughter, and let's start looking at how we can use this for vibration measurement. Okay. So this is me pushing her face back and forth like this, and we're tracking the point on her nose like this. And you can see the motion of her nose back and forth as that face is going back and forth. So that's the displacement in the z direction. As I said, this is a three-dimensional technique, so we can also get that measurement. So this is her rocking back and forth, and now we're looking at the measurement in the in-plane direction, not the out-of-plane direction. And we can do the same thing for the y direction as well. So maybe a less interesting structure is a dryer panel. This is a dryer, and so we patterned it. We're using a pair of high-speed cameras. We have a mechanical shaker here that we're exciting it with, and we wanted to look at can we use high-speed cameras and can we use low-speed cameras, and can we compare those results. The difference between these cameras are fairly inexpensive. These high-speed cameras are quite expensive, and so we'd like to be able to use this technique as well. The thing about measuring for vibration is when you're using vibration measurement, you're typically using accelerometers. Okay? And accelerometers measure well when the frequencies are higher, okay? Because there's an omega squared term with the acceleration. This technique measures displacement. Okay? So if you can measure with acceleration, and if you're measuring displacement, you have to divide by omega squared. Okay? And so it becomes more sensitive. The critical thing is displacement, and for vibration, there can be very low measurements. So we have to be mindful of, is there enough displacement for the vibration you're interested in? I'm going to skip over the filtering part, and I'll talk about phase stepping for a second. One of the things is when you measure vibration is that the structure of interest is moving fairly quickly. So you have to be measuring at a certain rate of speed. And if your cameras are not moving fast enough, you will get what's called aliasing. What we can use is a technique called phase stepping. And so we can artificially alias if, let's say, the structure is vibrating at this fast rate of speed. Well, my cameras can't sample that fast. Okay? I have to sample at least twice that rate, at least twice that frequency to get a proper measurement. Well, my cameras can't do that, so how can we do this? Well, we can artificially alias. If we know that the signal is periodic, then we can sample and we can provide a small phase shift in the signal. And then we can sample, and then what we can do is reconstruct a signal. So one of the things we did was explore this technique using low-speed cameras to measure a high-speed event. So this is that panel. This is basically the first mode of vibration, the second mode, and the third mode showing. And I'll show you better. You'll have a better idea if you see it visually. So I'll demonstrate that. So this is an example of how that panel is vibrating in its first mode. And I don't remember what the frequency was, but you can see that these two corners are moving together. They're out of phase with these two corners. So that's essentially what's called the first mode of vibration of that panel. Now, if I was to use, how would I get this full field vibration? There's several different ways. I could use accelerometers, but I would need to put accelerometers at different locations, or I'd need a lot of them. That would mass load the structure, okay, and give me an incorrect result. Or I could move an accelerometer from point to point to point to point, but then it would take a long time to do that measurement. We did this measurement in about, once it was set up, it took us about 5 minutes to get this result. And so we knew that at this frequency, this was the first mode. So let's just compare it to the second mode of vibration, which is very different. Okay. And again, this was done a while back, so we got a lot of dropouts and we were a little bit lazy about patterning. This is an example of how we didn't use flat white paint, so we're getting high reflections, and so we're getting some noise. Anyways, this is what's called a drum mode. You can see the pattern is very different than what we saw before. So this graph basically shows that we were comparing a low-speed camera technique using phase stepping with high-speed cameras. We basically got the same result, okay, for the different modes of vibration. How we compared that was what's using the modal assurance criteria. That's the equation for it. I'm not going to go into details about that, but it's a way to compare. Now, what's really important here is that if you look, this is what's called a finite element model of that panel that we had. And for a finite element model, you get all these little nodal points, which represent nodes of your finite element mesh. Okay, these are the experimental measurements that we got. Okay, and so we're getting essentially as many. The spatial density of our measurements is as high as the nodes, the number of nodes in the finite element model. So we're able to do very good correlation between one model, between the analytical and the experimental results, and that's basically what's shown here. So we have, it's very easy to do a comparison. So here's the correlation between mode 1, mode 2, and mode 3. This is the modal assurance criteria. We're getting on order of 98 to 90%, and it drops off a little bit with higher frequencies. The correlation to the finite element model, this is three-dimensional measurement of that. And then we also compared it to other techniques. This is using an impact hammer test. This was using a scanning laser vibrometer test that we had in our lab as well. And we're getting correlations, again, 96%, 98%, etc. So it's very good correlation between the two techniques. So if we did a traditional measurement using an impact hammer and an accelerometer, these points represent what you would typically measure. So you're getting maybe about 20 points or 30 measurement points on this panel. Here, using digital image correlation, we have 7,000 points to compare it with. We have much higher density of points. This is an example. This is if we look here, this is an Apache helicopter. Okay, and this is the wings. These are the stores where they hold whatever missiles and bombs and that sort of things, or fuel. And so if you look, this is the wing, this is the upright the wing, and if we pattern this area, oops, let me back up. We pattern this area of the wing, okay? This is basically the full field measurement that we got. If we tracked a single point, that's this one point here, what we did was we impacted it, and we wanted to see, can we measure the transient vibration? Well, sure enough, here it is. Okay, this was the impact, this is the vibration. We've got a damped, free oscillation of that structure. This is a small helicopter model that we had in the lab, and what we're going to do is look at the three first peaks, 6.5 hertz and 8.8 and 22.5 hertz. So let's take a look at how it vibrates. So here's the first mode. Okay, this is basically what's showing here is that this is red, that's blue, this is red, that's blue, etc. This is what's called the rigid body mode of that helicopter. So it's basically moving back and forth like this. If we look at one of the next frequencies, this is the next one. This is at 8.8 hertz. Okay? If we look closely at the tail, this is kind of a torsional mode. That tail is twisting like so. And then likewise, if we look at 22.5 hertz, the pattern looks very different. Okay? This is a breathing mode of that helicopter tail. So, in a few minutes, once we set this up, in about half an hour, we had these experiments, and we're able to physically understand what's happening with the structural dynamics of the entire thing. Another thing that you can use this for is what's called normal mode testing. So if it's vibrating, we can trigger off, if this is the accelerometer signal, we can trigger off this peak. We can trigger at that cycle, take one image, and with that we have the entire image. We have the normal mode for that structure, and I'm going to demonstrate that in a second. This is another structure that we tested. This is what we refer to as the base upright. This is a panel here. And so we're going to look at a few different areas. You can see there's pattern here, 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 and here. This is a zoom in on one of those patterns. So you have the digital image correlation pattern, and then this is an optical target. We're going to look at the comparison between those as well. So for this acceleration, here's the accelerometer signal, and if it peaks right here, we can take one snapshot, one picture there, and we can get the mode shape of that structure. If we look at these dots represent each of the center of those facets that I talked about previously. And so we're getting, I don't know how many, we got a few hundred points there over that one little region, and that region is about that big. So we're getting a lot of information in one little location. This is a comparison between the finite element model and digital image correlation. So the gray represents what the finite element model predicts. The red, these are the red patches. Now they look like one big blob, but really there's hundreds of points in those regions. So that's one of the modes. And again, the MAC is 99.3, so we have 99% agreement between the finite element model and the experiment. This is the second mode. Again, very good correlation. Now, what we're going to zoom in is on this right here. This is a nodal line of that vibration. And during the node, at the nodal line, there's very little displacement. So, as I said before, here's the node, here's that center location. Okay, you can see that there's some error, some deviation between what it really should be and what it actually is. We know that these points are, it should be a nice smooth surface, right? Because it's a flat surface, and we're not getting that. And the reason is because the displacement is very small. And as I said, this is a displacement measuring technique, and so if there's not enough displacement, you're going to get noise in the signal. Those other centered optical targets that I talked about, again, this is a comparison between those optical targets, looking at those on the structure. And again, 99.9% agreement between the model and the experiment. Mode 2, very good agreement between both of those. So that's pretty much what this basically says. It says, hey, we've got good results and comparisons between all of those. So now what I'm going to do is I'm going to switch gears a little bit and talk about some of the research that we're doing on wind turbines. So this is a small wind turbine that we have in the lab. This is actually a motor, so we're actually driving it. It just makes it a lot easier to do measurements on it. And so we're going to present some results on that. In this we have 3 mechanical shakers, 1, 2, and then another one back here. And we're exciting the structure. First we're doing it non-rotating, and then I'll show you some of the results with rotating. These are basically the modes of vibration, the different frequencies that correspond to the modes of vibration of this wind turbine. We're going to look at the first 3, and they're very closely spaced, 16.9, 17.1, and 18.1 hertz. They're very close. So here are basically, using a scanning laser vibrometer, this is the measurement you obtain with the different mode shapes, mode 1, mode 2, and mode 3. And again, they're very closely spaced together. As you get into higher frequencies, it starts behaving a little funny. Okay, so this is an example. What we're doing is we're comparing digital image correlation with a scanning laser vibrometer. The laser vibrometer is a traditional, more accepted technique for measuring vibration. This is a comparison of those two techniques. Now the blue, you can barely see it, but there's a blue frame here, a wire mesh. That's the experiment from the laser. The red dots, again, I showed you, here's thousands of points on each of the wind turbines. And we're comparing those two, and we've got a MAC value of 99.3 comparison between those two measurement techniques. So that was for a static measurement. Now what we're going to do is look at we're interested in not just static measurements, but we're interested in rotating measurements. And so let me show you that. Okay, so we started off a few years ago with a little fan like this, and as it's spinning around like this, we can track the motion of that fan as it's spinning. Okay, well, it's not spinning yet; it's just moving around. But we're going to do the same thing, and so let's do that. So what I'm going to point to you is there's 3 blades on here. There's a red blade, there's a yellow blade, and a black blade. And they correspond to these three curves down here. So you have the red, yellow, and black. The red and yellow, those two, you can see that they're essentially in phase, and they're essentially out of phase with that black blade. And let me show you the video for that as well. All right, so this is the blade spinning. It's spinning actually at about 1,080 RPM. So it's pretty quick. It's moving along. And although it doesn't look so fast in the image, but it is actually moving fast. So you can see these two blades are moving together, okay, and the black one is out of phase. And we're tracking those targets. So it's kind of hard to tell what's happening physically with that fan as it's spinning. So what we can do is we can derotate the image. Because these are digital images, what we're going to do is derotate them. Okay? And so let's pretend you're a little fly or an insect sitting on the center of that hub. Okay, you're sitting right there and you're spinning around as those blades rotate. As they do, you'll see these two blades. Here's that yellow blade, here's that red blade. It's moving together. It's moving essentially out of phase with that black blade. Okay? So I'm not aware of how else you can make this kind of measurement. And so when we did this test and we were successful at it, we said, wow, this is a great technique. What else can we use it for? So, all right, let's take a look. This is that wind turbine again that I showed you. Before it wasn't rotating, but now it is. And what we're doing is we're tracking these points, these optical targets. You can see those targets in there. Right now we're looking at the in-plane vibration. Okay, so if you had circular motion, and if you just looked at a component of that circular motion, you will get sinusoids. Okay, so if we track one point on here, that's what's showing. What we're doing is basically showing. Let me show it here this way. We're tracking one point on here, and as it rotates around in a circle, if I looked at one component of that, the x or the y direction, then I would expect sinusoids, and that's what we're getting here. We're looking at the in-plane motion of that structure at 3 different points. Okay. We can also look at the derotate. No, that's the same thing. Okay. All right. So this is the same thing, except we're using arrows to indicate the motion. This is again the in-plane motion of that wind turbine as it's rotating around. And again, physically, if it's moving in a circular motion, and if I'm looking at a component of it, I would expect there to be sinusoids, and that's what it is. So physically, I'm getting a good idea, I'm getting a confidence that this technique works. Okay? But for vibration, we're more interested in the out-of-plane motion. So let's take a look at that. So that's what's shown here. Here's that rotating blade. This is the out-of-plane motion of those blades. Okay? And we're tracking the 3 outer points that are shown here, and that's what the 3 points. So the vibration pattern is relatively complex, okay? And so these are, we can do the same thing with this, except now we've derotated the image, and now we're just looking at the components as it's spinning around, okay? So it's a little bit easier to kind of visualize what's happening with the different blades. So if this thing was just spinning around, it's impossible, especially visually, to tell what's going on. But optically, using these cameras, we can. So this is another example. What we can do is take that image, take that data, and derotate it. This is physically what's happening to that blade while it's spinning at about 18 hertz. Okay? So this is the complete motion of that wind turbine blade as it's rotating. Obviously, we're interested in this for wind turbines, we're interested in this for helicopters, and we're also interested in this for underwater propellers and that sort of thing. So. Okay, I'll skip over this. Well, I'll show you. This is an example of a test that other people have done. This was a large 40-meter diameter wind turbine. This was done in Europe, and this was an emergency stop that was done of a wind turbine. So basically, while it's spinning, if like something goes wrong and you want to stop it, and you want to be able to stop the wind turbine quickly, so that's what they did here. And then this is the resulting transient motion after that stop occurred. We're hoping to do a similar test. We're actually working on that right now, and we'll be doing a test similar to that sometime next year. So, as I said before, the test, this this technique requires some kind of pattern that you apply, either optical targets, or the structure has to have an inherent pattern, or you have to apply it. Okay, so this is the base of a 9-meter wind turbine blade. This test was performed at the National Renewable Energy Lab in Colorado. This is one of my graduate students who is applying the pattern using markers. And so you can see the dots that he put on. Now this blade is 9 meters long, so there's a lot of dots to put on there. So it helps to bribe your student with a case of beer and a few markers, and it enhances the stochastic pattern that you get. So once you make that image, if we're looking just at the root section, which is basically shown here, this is basically the image, that 3 different views of that blade that you get. So let's take a look at some of the results. This is the base of that blade. This is a 9-meter blade here. We're looking at this part right here, and you can see this is what we did in this test. Was we loaded it from 0 up to about 400 pounds in stepped increments. So it went from 150 to 250, etc., all the way up to 400 to a peak. What we're showing here, this is the deflection at 400 pounds, and then on the underside. This is the top side, this is the bottom side. On the bottom side, there was a crack that was located right about here, and you can see visibly, just by looking at it, you couldn't tell that there was a significant change. But by using this technique at about 400 pounds, we have a huge discontinuity in the shape of that structure. And so let's take a look at the video of that as well. And what I'm going to show you is basically the blade is being loaded up. Okay. Gets to about 400 pounds, we get this large discontinuity in the shape, and then it's unloaded again. Okay? And the other thing to point out in this is that at the beginning of the test, we had 0 deflection. At the end of the test, we have, I don't know what the unit's, millimeters. So this is half a millimeter, less than half a millimeter. So at the beginning to the end of the test, we had a plastic deformation or a physical shift in this test setup that was on order of half a millimeter. Think about a millimeter. And that's almost, you can barely tell that difference. So that's an example of the test. Now if we look, that was displacement. If we looked at strain at those 2 sections, this is the strain pattern on the top surface of that blade. Again, you can see that there's something going on here at that location. This is the underside. This is the strain pattern. Clearly at that location where there was a crack, we're getting a large amplification of the strain that exists. So you can see how this could be used for perhaps structural health monitoring. You pattern a surface or a wing or something like that, a vehicle. Okay, it goes out, it does something, it does its mission, and then it comes back. You take another image of it, just a snapshot, a couple of pictures, and then you can compare what was the change in the structure before and after. And so that's how we hope to exploit, to use it for structural health monitoring. One of the things that we're going to be looking at this technique is for bridges, how bridges change over time. And how one of the studies that we're going to be doing is basically we're going to image a bridge, and then we're going to go back a month later, go back 6 months later, and see how the bridge changes over time. This is that 9-meter blade that we patterned. So there's a lot of dots on there that we applied to this surface. Okay, and what we did, as I showed you before, it was not possible to take a photograph like this because the testing facility that we had, the ceiling of that testing facility was probably about the height of this room. And we had a 9-meter blade that was sticking out. So imagine taking a digital camera and trying to take a picture from the top of the ceiling down. You can't get the whole 9-meter blade. So what we did was we took 16 different images. We stitched them together. And so here's the complete displacement of that 9-meter blade. And so we're able to get the full field displacement measurement. And likewise, we could do the same thing with strain. So that gives you sort of a summary of digital image correlation, how people typically use it, and how we're trying to exploit it for vibration analysis and also for structural health monitoring. It couldn't have been possible without the help of my collaborators and also the people who have sponsored, or the funding agencies who have sponsored us, the Army, National Science Foundation, Department of Energy, National Renewable Energy Lab. So with that, I acknowledge the people who have helped me and have supported our work. And with that, I'll answer any questions that you guys may have about this. So thank you very much.
Well, thank you for a very fascinating talk. I'm wondering, this technique, it would be possible to use it to check sort of the damage to the structural integrity, like say corrosion?
It certainly can be if there's a change in
Let's say when you have corrosion, you have a change in the shape or something, some kind of aggregate material building up. You certainly can detect that. Okay, so that's one way. If there's a crack or something like that, then you can measure a change in strain. But you're limited to 50 microstrain. So whether that's enough or not, I don't know.
Because I think Power Gen at one time was looking at the loss of their the blades in their turbines, probably because of corrosion, and they wanted to get some way to pick it up before they could steer the corrosion in the eye.
Right.
I wanted to also ask you mentioned that the field of view, that sensitivity is contingent on the field of view. Before you start doing any test, do you optimize that field of view to get maximum? I know you're getting fantastic Mach values, which in a sense is a reflection of your sensitivity.
Right.
But do you have to do any extensive optimization of the field of view, or does it come with experience?
Usually we don't have a choice. We usually, like if we're doing a structure, we say we want to measure a bridge, or we want to measure a turbine, or we want to measure some part, okay? And so it's determined by the application. Yeah. So if we're interested in a field of view like this, we can compute what the sensitivity is. So it's not like we can, the only options we can change are we can improve the resolution of the cameras. That significantly improves the sensitivity. So one of the nice things about this technique is that most of the results I showed you were using 2 megapixel cameras. Today, 12 megapixel is pretty common, and who knows, 10 years from now, how many megapixels we're going to have. So as this digital technique, the resolution of the number of pixels of the cameras increases, this technique, the sensitivity is only going to get better. And so the field of view, or the sensitivity, is dependent upon the field of view. And that's something that, basically you have to say, okay, like if you're trying to measure an entire ship, well, you're going to get, one, you can't pattern it, it's not practical to do that. But if we're interested in a specific region that we know that's going to be critical, we can pattern that area, or perhaps look at some small regions or stitch images together in that way.
Mm-hmm.
So.
I just want to clarify something that I'm understanding what I think was going on here. When, in that one slide when you went from node to node pairs, I'm assuming, and I could be wrong, you'll correct me, that this was the analytical versus experimental comparison to get the map.
Exactly.
To get the map.
Right.
One last, in a sense, not really facetious question, but given the experiments you did with your daughter, can this be used in plastic surgery? So I'm not going to be sublime to do ridiculous with corrosion to plastic surgery, but because one of the complaints about surgery is that people have this frozen face look. And looking at the strain centers there,
Well, one of the things that people, it relies on a pattern. Okay, and so if the pattern, let's say you have an initial pattern, you take a measurement, you can get a shape before, but then that pattern has to be the same if you want to get a strain. What I know Gillette is a company that makes like razors and that sort of thing. They wanted to quantify the performance of their, those little lubrication strips that they have and how well they work. And so as you pull on them, how well does it strain the skin? So I know that they've used that.
On the face.
Exactly. So we've used it on a face. I know other people are looking at this technique for spine to see how
straight. Then the plastic surgeon can understand what you can do. If a part is very straight, you don't over tighten that part.
Yes.
Yes. that sort of thing.
So what you could do, one thing you potentially could do is you could apply a pattern to somebody's face. You could look at how their face changes when they smile.
Yeah.
And then after the surgery, you can see how the face changes again when they smile. And then you can compare, well,
right.
So for example, if you had Botox basically anesthetizes your muscles and paralyzes them, right? So if you had Botox injection, you could say, okay, you can clearly indicate that this part of the muscle is not moving, or your forehead or something like that.
But I suspect that a straight pattern on a face might be almost as individualistic as fingerprints. It might be impacted by your bone structure, by even the way you smile, by your teeth. One never knows. You know, perhaps you could try it again in a few years.
That certainly is possible. That certainly is possible. Yeah.
I'm intrigued by the use of the technique to compare finite element images to what you see in terms of real object displacement. So to find some benchmarking method for. So we use finite element method, of course, very extensively. One of the issues is the cell size that one chooses is often a question. That is, you would like to use the coarsest cell size that would give you a reasonable result. So if one has a model that you can, for example, subject it to a thermal pulse and look at those deformations, then when you do the finite element method, you can sort of bracket which cell size gives you something close to real deformation. Because this is, people produce a lot of pretty pictures, but there's always a question of, is this real?
Right.
How close is this?
Right. So someone made an interesting comment a few months ago. I was talking to someone, and they said they had all these computational models. Mm-hmm. Okay. But if there's no tools to validate them, then they're just video games.
Right.
In terms of measuring shape or changes in the structure to a known applied load, it's a great validation tool.
And I think 50 microstring is a reasonable.
That's pretty small. It's pretty small, but there are some situations in which you need less.
Even finer.
Right, but for the most part, 50 microstrain gets you quite a bit.
So as far as you know, no one is really pushing the envelope in terms of that application.
I'm not familiar. I don't know exactly. I lost my image, but I'm not 100% sure. We validated our vibration models with it. And compared it with that. Because when we first started doing this technique, nobody else used it for vibration analysis. And so we wanted to see, without doing some kind of validation of the technique and gaining some confidence in this, people look at it. The first time I saw those images of that airbag or something, I was like, it seems almost like unbelievable, because just once we set it up, we took 2 pictures. There's the shape of the airbag. And it seemed almost too good to be true. So when we started doing the dynamic measurements, we definitely needed to be able to convince people that this technique is appropriate. And so that's why we've compared it to a laser vibrometer, accelerometer measurements, and finite element model as well. So I think it's an excellent tool for validation. If you can get an experiment that you can model correctly, the boundary conditions are critical with finite element models, and the loading that you apply is critical. If you know those and you have a good model, then you can validate it.
I'm just curious, what is the wind propellers? What are they made from? Is it a composite or is it a solid?
The small ones are made out of plastic. Okay, they're, I believe, injection molded, because they're only 1.3 meters in diameter, so it's about this big. Each blade is about that long. As you get the other wind turbine that we have in the lab, it's again, it's about a 2-meter blade, one blade, so it's 4-meter diameter, and those are also plastic. Once you get to a larger blade, 9-meter blade, that one's made out of basically fiberglass and a fiberglass composite. And then most commercially large wind turbines are made out of fiberglass. Some are made out of carbon fiber, but most, I would say 90% are fiberglass.
Wouldn't the response be different in different types of material?
Of course, yeah. It is, because obviously if you have fiberglass, it's not as stiff as carbon fiber, so you're going to have a different response, much stiffer response.
So I guess you have to populate different composites and different materials to find out what the reaction will be.
Yeah, that's something, there's a whole issue with modeling, modeling carbon fibers, and with wind turbines, they're made out of, you have a spar cap and a central spar that's typically made out of balsa, which is laminated with fiberglass. And then you have the layup of all these different layers of fiberglass. And so modeling is a challenge because you have an epoxy, you have the fiber, you have the resin, whatever, and then you have the bonding issues between them. Then you have balsa wood too. And so what we're doing this right now in our lab. We're trying to do this with plates and panels that are simple. We have a fairly simple model of this composite layup, and we're seeing very big differences between this, just for a plate, a plate that's about this big, and the mechanical properties are really hard to model. And I don't know how they're doing it for a large-scale wind turbine or something like that, but yeah, it's difficult to model these things.
Then there's the noise reduction issue. In wind tunnels, that's a big issue in the development of the wind tunnel.
I'm sorry, wait.
Noise reduction.
Yeah, I think that's an issue for some applications. If a wind turbine is fairly close, there are some issues with infrasonic noise and that sort of thing. But for the most part, I think these things are fairly quiet, relatively quiet. I know the ones that I've been standing next to, the thing has been there. I can't hear it. I'm like 200 feet away, and I wouldn't. If I turned around, I wouldn't know it was there. So.
The other question is, my background is managing the construction of nuclear power plants, and I was on I think maybe one of the first teams that put together, that postulated how to contain in a worst case scenario accident population. And what we did was work with the design engineers. They came up with a 6-foot thick wall thickness, 200-foot diameter cylindrical building with a dome on the top. And we had to prove to the world that if there was a worst case accident, that building would retain the steam that would come out of the reactor.
Okay.
And what happened was we postulated that the maximum pressure would be about 40-something psi. And so we tested the building up to 54 psi.
Okay.
And we actually put infra wire with strain gauges, hundreds and thousands of them all spiraling up and down the building on the inside.
You could have used digital image correlation. In fact, one of my colleagues, he did a water, a 70-meter water tank, and it's a hot water process tank. And so what they wanted to look at was exactly that. They wanted to look at the changes in the shape of the tank as it was filled, because it apparently can fill this pipe, maybe that in diameter. It fills a swimming pool, like a swimming pool, in about a minute. Okay, so that's a lot of water. And so it's going, and it's bulging the tank as it's going. So they wanted to measure the strain and the change in the shape of the tank. And so with the strain gauge, you either have to have thousands of them, right? Right? And you need a huge data acquisition system, right? Or you can put on these targets and measure the change in the shape of that. So that's exactly what he did. And he got great measurements. I have actually an image, not on this computer, but I have I can forward that image.
This was a heavily reinforced, 6-foot thick wall thickness. 200-foot diameter, going up in the air. And we had pressure to twice the pressure of a car tire.
Okay. Yeah. So similar kind of very analogous thing. Tim Schmidt from Trillium Quality Systems, he was working on a nuclear containment vessel. Okay. And they wanted to monitor the containment vessel over a period of years. So they did the first measurements apparently this year. And now they're going to measure it every year for the next 20 years or something like that to see how it changes. And so that's a good application to see how it deforms and stuff like that.
We actually had to hang Muslim chairs all around the building and climb up and photographs all the cracks as the building was growing.
Okay, yeah.
And the designers would not show up on the site, and we didn't know why they would not show up.
Okay.
They were scared that they would go up. we didn't know that.
Right. For measuring crack growth, if you see a crack and if you wanted to know if it is growing or not, this is a great way to do it. You can pattern the area of the crack, take an image of it, come back a month later. Has it changed? Has it grown?
Yeah.
And that's a great way to measure it. You can get terrific in-plane strains and that sort of thing.
When it was deflated, it didn't fall back to the original size.
Oh, is that right?
Yeah.
Interesting.
Well, ladies and gentlemen,
May I ask one quick question? Trinidad is very earthquake prone.
Is that right?
Yeah, and very, very earthquake prone. And I see buildings on the side of the hill with thin columns that are sitting on a 4-story building on top of it. And I think that, I wonder if anyone has done research on these columns. Are they coded, and what design basis do you use for those columns? Because if a real earthquake comes, I would think that maybe 70 to 80% of those buildings will crumble, will fall off the side of the hill.
I think that you really doing some research on that now. I think they're doing some research on the ties, some ties in the columns. that apparently is the weak spot.
But if you come up with a design table that says this is how much steel you should use for this heavier building, and a column that is
joint ties.
You have what is called a slenderness ratio in a column. And the slenderness ratio on these columns on the hill and the weight on top of it, it means that if there's a side movement, the concrete, there's flexible concrete today, but they don't use flexible concrete. Those things go beyond a certain degree of rhythm, it's going to crack up. And the building is going to...
Sorry, I think that big enough is going to
Excuse me?
Maybe a big is big enough. High magnitude is going to match that. All right, then, thank you, Professor Niezrecki, and thank you very much.